the transformer. And in your parts kit, everyone's got a transformer there. And the transformer is going to step down the voltage. So we're going to be taking our transformers, we're going to be plugging it into the wall outlet. We're going to get plugging into 117 volts AC. And then it's going to step down the voltage to a certain level. And then give us the new low voltage output going into our DC output. So we're gonna come in with our high voltage, step down, go down to a low voltage AC, and then we're gonna rectify it going through the diode. And then this is gonna be our load. That's gonna be our load. So that's gonna be our DC voltage. So we're gonna be converting our AC voltage into a DC voltage. So the step down transformer then is going to have a certain amount of windings. Depending on what the ratio of the windings is going to determine what the step down voltage is. So for example, we'll use some nice easy numbers here. Totally electrically isolated from one another. We got one set of windings on the core that's on our primary. And then we have another set of windings on our secondary that's wrapped around on the same core. And then, remember as we started talking about our magnetic fluxes crossing over the coils and stuff, it's going to induce the voltage and stuff. So, on our primary, if we had, for example, if we had 120 volts on our primary side, and we have 10 windings on it, and then and this is just a ratio, there's going to be several hundred windings on there, but just for the ratio itself, if this has got 10 times more windings than what the secondary does, then all we're really doing is we're taking our 120 volts and we're going to divide that by our 10, and that's going to give us our ratio. So then on our output side, we would end up with 12 volts AC. Okay? So it's just basically a 10-to-1 ratio. I'm going to have 10 times more windings on here, meaning that my voltage on here is going to be 10 times more than what my secondary is. Now the transformer's power is always the same. It doesn't matter if it's on the primary or the secondary, but power is always going to equal on both sides. So when I'm using a step-down transformer and I've got 120 volts going on the input, this thing might draw. So we'll use our transformers that we got 1 amp transformers on our secondary. So if I have more voltage on my primary than I do on my secondary, then what I lose in my voltage, I gain in my current. So if I'm taking and I'm putting a load on here on my secondary, and I end up drawing 1 amp of current, then my current on my primary side is going to be less, and it's going to be less by 10 times. So then I'm going to end up with only 100 milliamps of current on my primary. So whatever I gain, so if I gain current, then I lose my voltage. If I lose my voltage, I gain my current. And so then if we ended up doing the Ohm's law on our power where we take V times I, then I'd end up, so for example, if I take 120 volts times 100 milliamps, what would I get?
12 watts.
12 watts. If I take 12 volts and times it by 1 amp, what do I get?
12 watts.
12 watts. Okay, so power is always equal on both sides. On an ideal transformer, there's some losses and stuff like that because of the resistance of our windings and stuff like that. And so we're going to, so when we're building a power supply, so that we can, like when we're using the Midax or the power supplies on our workbenches and stuff, we're taking 120 volts, and then we're dropping down the AC voltage, and then we're going into a rectified circuit, so we end up getting our lower voltage. So that's what the transformer is doing. It's just stepping down our voltage, and it's just all based on a ratio. If I wanted to, I could go ahead and I could do it the other way. If I switched this around before, here was this is my primary, this is my secondary. A transformer can work either way. So I could actually end up changing it around, put this as my primary, and making this as my secondary. And then what would happen if I put in 12 volts AC into this transformer, what I'd end up getting is 120 volts AC out. So I just end up doing 10 times more of my voltage. So a transformer can work either way. So, but then again, if I gain in my voltage, then I lose in my current by that same ratio. And then the power always stays the same. So yeah, transformers can work either way. And if anyone's seen that Jacob's ladder that it's shown out in the lab there with the big arc there, the two rods and the arc goes up and stuff, that's what we're doing. We're taking 120 volts, and we got so we've got 120 volts, and then we got a 100-to-1 ratio on our windings and stuff. So I get approximately about 12,000 volts coming on my output, and that's what's creating that arc, because they got such a large amount of voltage and stuff. So it's just so a transformer can really work either way. All right, then so those are going to be your two. Those are going to be the two colors, whatever colors you have. I know we all have slightly different colors, but the two that are the same, those are going to be your secondary. That's going to be your secondary voltage. And on our transformers there, this is a secondary. It says 12.65 volts. So I put in 120 volts. I'm going to get 12.6 volts output on my secondary. Then what the third wire is just a center tap, and it's just tapping off halfway into the coil. And so then if I use that as a reference, if I go from here to here on our transformers that we got in our kit, I'd get 12.6 volts. If I use the center tap, then I get half my voltage. I'm only going to get to 6.3 volts. I get 6.3 volts there, and then I get 6.3 volts there too. So and you'll see in some of our power supplies that we're going to have be utilizing that center tap for our full wave rectifier. All right, so any questions on the transformers? That's pretty straightforward. I think I signed chapter 14 for you, didn't I? Yeah, so you should have read through that. So just kind of a quick recap on that. All right, so our first step is, we're going to figure out, what is our, if you're analyzing it, you're going to find out what your ratio is and stuff like that. Then you're going to find out what your secondary voltage is. So on this particular circuit here, I'm going to just tell you what our secondary voltage is. And our secondary voltage on this one is going to be, our output on our secondary voltage is going to be 20 volts AC. So if I put on 117 volts AC, I'm going to get 20 volts AC on the output of my secondary. So now our first step then, so now we can kind of eliminate this. Remember, this is electrically isolated. That's not even part of our circuit anymore. So the only circuit that we're really worried about is the stuff that's on the secondary side of our windings. Now remember, 20 volts AC, remember that's the heating effect of a resistor. That's an RMS value. That's an average. So what we want to do is we want to get the absolute value of what that AC waveform is. So what we want to do is we want to convert this into our peak-to-peak voltage. So what's 20 volts how do I calculate out my 20 volts AC to a peak-to-peak voltage? Yeah, so you can take 20 volts AC, and you multiply it by 1.414, or what I always use is, the number I always use is the 0.707. That's the only number I ever remember. I don't try to remember any number. So, but this one works too, and this will give us our what voltage then? What unit?
Volts peak to peak.
Volts peak.
Volts peak. Yeah, remember, and that's why I always like, because if we're going to convert our volts peak into an RMS value, we multiply it by 0.707, right? That's how we get our RMS value. So if I know that, if I just remember that, then I know that if I take my RMS value and divide it by 0.707, then that'll give me my volts peak. Then I just have to do it and multiply it by 2.
But up there, it's already rated peak to peak if you do the top one.
Oh, let's see.
Go ahead and do it. You got calculated, Ron?
Or no?
So let's see. Yeah, let's see. I think this will go because of dividing. I think this number, and this number should come out the same. They do, right? So that means that this number here is still calculating out our volts peak. This is why I remember this formula. Then I don't have to try lots of these things. If I just remember the 0.707, then I either multiply it or divide it, then I always know that I'm going to always come up with my volts peak. Yep. So this one is also come up with our volts peak. So then we have to take that number and then multiply it by our volts peak, and multiply it by 2. So what do we end up getting then for our volts peak to peak? Yeah, and that gives you your peak to peak voltage, right? Well, once we got our voltage peak, right? Okay, remember. Okay, go back to AC. So if I have here's my waveform, right? So my volts peak is from here to here. My volts peak to peak is from here to the top of this peak, and that's my volts peak. Okay? Yep. So what do we get for our volts peak to peak?
$56.56.
56.56 volts, and then now it's peak to peak. So our 20 volt AC is equal to 56.56 volts peak to peak. So I'm going to have this. So when we're first analyzing these circuits, we're taking a look at the waveforms. So we know that I got a waveform here that's at 117 volts AC, and it's going to be going up and down. I'm going to have one half of my peak is going to be going positive, and then my other half of my peak is going to be going negative. So when we're analyzing these circuits, we always analyze the first alteration, and then we go to the second alteration. So if I look at my first alteration, here's my first alteration right here. Now, that first alteration, what's the voltage of just that first alteration? And that's going to be my voltage peak.
28.28.
Yeah, so it should be 28.28 volts peak. So we're going to analyze that first half of that cycle. So if I put my ohm meter on here, here's my reference to ground, here's my red lead, here's my black lead, and I'm measuring on the secondary side of my transformer. I'm going to measure my 28.28 volts peak to peak. Or if I use what I really ideally would like to use is my oscilloscope. So I'm going to look at, when we're looking at AC waveforms, we're always using our oscilloscope. So this first alteration is going positive, and so my polarity across here is going to be negative, positive. So that's going to be my first alteration. It's going to be my polarity across my coil is going to be negative, positive. Because if I have my black lead here, my red lead here, I would measure a positive 28.28 volts peak. I'm measuring that first alteration, which is going positive. And then what we want to do then is so now we know our polarity across our transformer, we know what the voltage is, and then we want to kind of analyze it the rest of the way like we did with the rest of the diode. So what we want to do is we want to circle our active component, put in our polarities across there, because we need to determine whether if that diode is going to be a go or no go. So referencing it to ground, so here's my ground. And remember, we treat that diode as what when we first analyze the diode?
Open.
As an open. So we're just going to treat that as an open. And if I put my black lead on ground and my red lead here, what would I measure for voltage on my cathode side?
0 volts.
0 volts, plus or minus 0 volts. So that's our soft voltage. Then if I go over to here, and I bring my red lead over to here, what would I measure for voltage? Yeah, so what did I measure here?
28.28 volts.
Right. So what's my polarity?
Positive.
Positive. So this is going to be a positive 28.28 volts peak. Okay? So now we need to determine whether if that diode is going to be a go or no go. So is that diode a go or no go? That's a go. So that diode's a go. And it's going to do what?
Drop 0.7.
It's going to drop its 0.7 volts. Okay? Which way is the current going through the diode then? We know that it's a go, we know that we have current going through it, so which way is the current going through it?
Right to left.
Right to left. So then we know that my current is going from right to left. So I know that's my polarity, and here's my arrow, I know my current is going that way. So once we determine that, then we can go ahead and draw in our current path. So here's my current coming out of the negative side of my transformer, coming up to the ground, through my load resistor, through my diode, and then back into my power source. Okay? So now we need to determine what our output voltage is going to be. So I know that my current is coming through, going through my load resistor. The diode can always drop its voltage first, and then back to the source. So what would be my output voltage peak output be then?
27.5 base volts.
What it would be?
27.5 positive.
Positive 27 point what?
5.8.
5.8 volts peak. Okay? And that's going to be the same as what because that's what once that voltage of the diode takes its voltage first, the remainder goes across the load, and then the voltage across the load should be 27.58, If I measure across that, referencing it to ground, I would get a positive 27.858 volts peak. So that's going to be my output. So what my waveform then is going to look like is it's going to look, and it's only going to go up to a positive 27.58. All right. So that's our first. That's going to be that's our first alteration then. Then our second alteration then is going to go negative. Then our next alteration is going negative, and so the polarity across my transformer is going to change. So now my polarity is going to be positive to negative. So if I still keep my black lead on, my ground, bring my red lead up, I can see that I'm going to be more negative on my positive lead, and I'm going to read a negative voltage. And my negative voltage is going to be that negative 28.28 volts peak. So then we want to do the same thing now. We want to analyze our diode. I'll just write it up on the top. This is where colored pencils come in nice. So the green will be all our mixed alteration. So we know that my current's going to want to go this way. So if I do my soft voltage, if I bring my black lead on ground, leave that on ground, and bring my green lead up onto my cathode of my diode, what would I measure for voltage at this point? Assuming that diode is an open. 0 volts. Still going to be my plus or minus 0 volts. Then if I bring my green lead over to my anode, what would I measure for voltage? Negative. So now this time it's a negative 28.28 volts peak. Okay. So now we know that on my anode side, I got a negative 28.28 volts peak on my anode side, plus or minus 0 volts on my cathode side. Is that diode a go or no go? This time it's a no go. And if it's a no go, what is it going to drop for voltage? The source voltage. And our source voltage is going to be our 28.28 volts peak. Okay, so how much voltage is going to be remaining across my load? 0. So then I'm going to end up getting 0 volts across my load. And so then my output is going to look, for that second alteration that is going negative, it's going to look like that. Okay. So that's what our waveform would look like. If I put 120 volts or 117 volts AC into my transformer, my output would look something like this. It's going to go up to the positive 27.58 volts peak, go down, and then it's going to go in the reverse direction, and then my diode is going to act like an open, act like an open switch, and then let nothing out of my output go through. So then it's just going to be a waveform that's went up to a positive 27.58 volts peak, and then go into 0. So then when we're doing waveforms and we're graphing those waveforms out, then what we always want to do is we always want to graph out 2 complete waveforms. So that we can show the person that here's where it repeats itself. This is always going to be repeating itself. Now, one thing sometimes, depending on what our circuits are, sometimes we have to, so we kind of did this as an ideal circuit. If we were really to actually zoom in on this, on our transformer, or on our waveform, what we'd really actually find out is that, remember, our first alteration, it started out at at 0 volts, right? So it takes how much voltage does it take before we even turn on our diode?
0.7 volts.
0.7 volts. So that thing, if I really zoomed in on this area here, on that first instance, until that waveform gets up past that 0.7 volts, that thing is going to stay at 0. Okay, so I'm kind of zooming in on that right at the beginning of my waveform. It's going to stay at 0. Then it's going to go up, and then once it gets down to that below that 0.7 volts again, then it's going to go back down to 0 for that little instant. And then on this particular one, then it just is going to stay at 0 again until it hits that 0.7 volts. So when you're analyzing the circuits, and if you zoomed in on that little area, you're going to see that this thing really doesn't actually do anything until it breaks through that barrier potential of that 0.7 volts. And you can zoom in on that on your oscilloscope, and you can see that diode really doesn't start to bias until that waveform gets up above 0.7 volts. But in our ideal or ideal power supply, we just kind of treat it as an ideal diode. But yeah, you always have to make sure that we always are remembering that it takes that 0.7 volts before it turns on that diode. So then we have our two waveforms with a positive 27.58 volts peak, goes to 0, and up to another positive 27.58 volts peak. All right, so that's what our waveform looks like. And then what we want to do is we want to figure out what our DC average of this signal would be. So if I put a digital multimeter on here, what would I really actually see? Right now we're just looking at it. Here's what I would see if I had to use an oscilloscope. Now I want to see what I would get if I was using a digital multimeter. And this is where that number 0.637 comes in. And this is the one I said, well, we really have to hold off on, because if I average out this waveform, my DC average would be 0. Well, now since I'm bringing everything all positive, now I can actually get a real DC average. So what we like to use for our formula is what we do is we take our first two voltage peaks, the first alteration and the second alteration, and we add those two together. So we're going to just take our voltage peak plus our voltage peak 1, then our voltage peak 2. We add those two voltage peaks together, and then we divide it by 2. And now we use our number for our DC average of that 0.637 for our DC average. And that will give us what our DC multimeter would read using that. So if I take my first voltage peak went up to, and don't forget the polarities, it went up to 27.58 volts peak, plus what's my voltage of my second voltage peak? 0. Plus or minus 0 volts peak. Okay? So I add those two together, I'm just going to get my positive 27.58 volts peak, and divide that by 2, and then multiply it by my 0.637. What do I get for my voltage? 8.714? 784 volts. And remember, when we're talking DC, if you don't put a unit, we assume that it's DC. But if we want to kind of keep track of what all our voltages are, you know, if we're talking voltage AC, voltage peak to peak, voltage peak, or voltage DC, sometimes it's kind of nice just to put in that it's 8.784 volts DC. So if I were to put a oscilloscope on, I'd measure my positive 27.58 volts peak. If I put my digital multimeter on and set it to DC, I would measure a positive 8.784 volts DC. Okay, not a very clean DC power supply, but one with a DC average now. So then that's going to be what my voltage is going to be across my load then. My voltage across my load then is going to be 8.784 volts DC. Let's see, did I give you a resistance value? No.
No.
I didn't give it to myself either. Yeah, so it should be, yeah, so it should be a one kilo ohm resistor. So if I have a 1 kilo ohm resistor, then what is going to be my current at my DC level then? What would be my current then for my circuit here? So using your DC average, calculate out what your current would be. Milliamps. Milliamps, and that's our DC current. And then what would be my power then? So 77.16 milliwatts. And that is true power because we are going through a resistor, so that is in watts. Okay, so that's our powers. Alright, so then our last one then is what is our frequency of our ripple. So our ripple is the amount of voltage that we have from, and it's just based on amplitude. It's not really based on where it is on zero or anything like that. It's just the height of what our ripple is. This is what we can consider ripple. We're not referencing it to, because when we get into a full wave and stuff, we're going to see that ripple is going to have a DC offset. It's going to be riding up on a DC average. Here it's going from 0 up to 27.58 volts peak, then going back down to 0. And so the only thing that we're looking for is just the amplitude. No polarities or anything. We're just looking at where is it from the lowest point of that signal to the highest point of that signal, what's the amplitude of it? And so for in this particular case then it's going to be our 27.58 volts. That's going to be our ripple. All right, so then the frequency of our ripple then, since this is our ripple here, I have 60 hertz going in. What would be what's my frequency of my ripple coming out then? So if we were to, so sometimes it's a little easier to see it if we, so if we're graphing something, we're going to do two complete waveforms. So here's my source going in. So this is my VN, my 117 volts AC going in, and then my V out. And it's going to look like this. So that's going to be what my V out is. Here's my V in compared to my V out. So this frequency here is at 60 hertz. What's my V out going to be equal to for frequency? What's the definition of frequency?
Should be 60 hertz.
It's gonna be 30.
1 over the period.
Yeah, 1 over the period, or remember the definition for frequency is how many cycles I do in 1 second, right?
Yep.
Okay, so here I'm doing 60 cycles in 1 second. So here's my 1 cycle, right? From where it starts. So right before it starts to repeat itself. So that's 1 complete cycle right here. And we know that's going to be 60 hertz. So if I look on my output of my waveform, so I know that here I'm starting here, I'm going up, and then I keep on going, and then right at this point it repeat itself. So the time that it took for this is equal to the time that I did this. So what would be my frequency of my D out then? 60 hertz. So remember, one cycle is where it makes 1 complete waveform before it starts to repeat itself. And since the time on both is the same, I'd have 60 hertz. So my frequency ripple is 60 hertz. And as we get down and go through it a little bit farther, we know that the higher the frequency ripple, the better the power supply I have. All right, how'd that one go? So I'm going to repeat this one more time. We go back to it one more time. We want to go on to the next power supply.
Speak up or forever hold your peace.
Yeah, that's right. Moving on. The other ones are very similar. Yeah, this one, the first one is kind of, it's got so much other stuff in there, so. We got a lot of practice with doing these. All right, do one more here, and we'll take a break.
Yeah.
All right.
Yeah.
So here's our next one. This is one that's a little bit more. This is a very common power supply out in the industry, using 2 diodes and then the center tap of our transformer. So when we first are analyzing, figure out how these power supplies are working, get in the habit of drawing in circling your active components and putting your polarities inside the circle there for your active component. That'll tell you, definitely give you your direction of which way that current is flowing. So then our next step is, again, we're always going to analyze our signals by the first alteration and then our second alteration. So on our secondary transformer, we're just going to keep it with the same voltage so we can kind of compare the difference between all our different power supplies here. So we're going to use our 20 volts AC again. Okay, so the real main voltage, we know that my voltage peak is just going to be, my voltage peak positive and then my voltage peak negative. So all we really need to ever really find is what is our voltage peak. So I just wanted to kind of go and refresh our memory about voltage peak to peak and all the other units and stuff, making sure that we keep track of them and make sure we properly put our units on each one of our numbers there. So all we really need to do is we just can go right from our 20 volts AC and go right to 20 volts, or then calculate out our peak voltage. So what would be my peak voltage then for 20 volts AC then? What's my peak voltage? 28.28 volts peak. Okay. Okay. So then our next step then is that we need to get in our polarity. So we're going to take a look at the first alteration. So we know that the first alteration is going to be going positive. And so the voltage across my secondaries, we're going to start out as being negative and positive. Okay? So we know that we have, so from here to here, I know that I'm going to get my 28.28 volts peak to peak. Zoom in on this a little bit here so we can see it. So here's my okay, so now when we're using our center tap on the other one there, we just ignored the center tap. It wasn't connected to anything. It was just, the wire was just hanging there. So we didn't have to be concerned with it. Now, the ground becomes part of our circuit. So now we have to be aware of it. And it's going to divide up that coil in half. So we said that my polarity across the coil is positive, negative. And then when we divide this thing up, we know that I'm going to divide that up. And so it's like having two coils. And so my polarity across here is going to go negative, positive, and then the other coil is going to be negative, positive. Okay? So if I was referencing it to ground, like here, first of all, if I go from here to here, I'm going to get my 28.28 volts peak. Then, but if I reference it to ground, and going from here, I know that half my voltage has to drop across this coil. So what would I measure across this half of the coil? Yeah, 14.14 volts peak. And then the other half would have to drop across here. So if I'm measuring what the output of this secondary transformer is, I'm just bringing my red lead down to my black lead, so the first sign I see is going to be a positive 14.14 volts peak. So the output of that, referencing it to ground, is going to be a positive 14.14 volts peak. Then if I go to the other side, put my black lead on my ground and going over here, what would I measure? A negative 14.14 volts peak. Okay? So when we're referencing it to ground, we need to know what our voltages are across each one of our, across half that coil. Alright, so we ended up getting our polarity so we know that it's going that's what our polarities are going to look like across that coil with our ground attached to it now. Alright, so then we're going to treat those diodes as if they're opens, and then we got to bring in our soft voltages. We're going to need to determine if they're go or no go. So it doesn't matter which one you analyze first, but we'll just grab the most logical one, we'll grab D1, and we'll do our soft voltage for D1. So with my black lead on my ground here, and my red lead up here, what would I measure for voltage? Plus or minus 0. Good. Okay. Because it's basically, I just went, since that both the diodes are treated as an open, and if I go back down the ground, I know that my load isn't going to be dropping any voltage and stuff, so I know that I'd have plus or minus 0 volts going across that diode. Putting my black lead on ground and my red lead here, what would I measure for voltage? 14, yep, and it would be positive or negative?
Positive.
Positive. So here's where our clarity is really come into effect. Okay? So now actually I want to change the color here. All my soft voltages are green. Positive. Okay, so is that diode going to be a go or no go?
Go.
That one's a go. And it's going to do what?
Drop 0.7 volts.
Drop our 0.7 volts. Good. Alright, so we know that the current going through my diode is going from left to right or right to left?
Right to left.
Right to left. So there's my... So right to left. And so I know that my current is going through my diode in this direction. Alright? So we determined that diode is a go. Then what we want to do is we want to check determine our other diode. So we're going to put our black lead on here, put our red lead on our cathode, and what would I measure for voltage on this diode? Plus or minus 0. Okay, then on my anode side, what would I measure for voltage?
Negative 14.
Good. That's negative 14.14 volts peak. So is that diode a go or no go?
No go.
That one's going to be a no go. It's a no go, and it's going to drop source voltage of 14.14 volts peak. Okay? So what's going to happen is that just diode number 1 is the only one that's going to be a go. It's going to drop its 0.7 volts. And then the remainder is going to drop across the load. And then this diode here, while I'm on my first alteration of my waveform, this diode here is never going to turn on that first alteration. So my current path then is, I know the diode, my current is going through my diode. It's coming out of my ground, so my current path coming out of my ground is on this side of my transformer. This is the most negative side. So it's coming out of my ground, and it's going up through my ground, across my load, back up to here, and it's going to hit this first current node. Now we already said that this diode is an open, right? So there's not going to be any current going this way. So all the remainder current then is just going to go back up through my diode. It's going to go through my diode and then back into my source. So that's what so for the first alteration, that's what your current path is going to look like. Alright, so then we're trying to take a look at what our voltage out peak is going to be. Because we know that I'm putting in an AC signal, and I know that my waveform is going to start to look, it's going to be positive, right? So if I bring my red lead down to my black lead, it would be a positive, so I know that's going to go positive. And I just need to know what the height of that voltage peak is going to be. Positive 13.44? 4 volts peak. Okay? So then, that's going to be the height of my first alteration there. All right. So then, just to verify, so we know that this diode is a go. We know that we have you always want to kind of double check your work to make sure that this diode number 2 never did end up turning back on. So you always kind of want to double check your work to make sure that you don't accidentally turn on another diode accidentally after another diode turns on. So we know at this point here I'm going to have a positive 13.44 volts peak. So my voltage on my cathode side of diode 2 is going to be what? What would be the voltage on my diode number 2 for the cathode side?
Positive 13.44.
Yeah, so positive 13.44 volts. Treating this as an open, what would it